everybody, and today we're going to be doing episode 11 of my biochemistry series. And now this is where primal is going to be very important. It is a 3D protein building structure, and I will tell you how to download it and how to use it. I can use now if you figured out how to do it from the beginning of my series, you probably already know how to do it. But for those of you who are new to it, here's how to do it. So firstly, you need to go to the Primal website. You'll see something here. Then you scroll down to download Primal. Next, you will want to choose on which ones. I'm on the Mac OS, so I would click this. If you're on the Windows, you do this. And if you're on this Windows, then you do the password. And if you're Linux, you do start. Then, now once you've downloaded, sorry for that background noise, you open it. And then you shall drag it. This is for the Mac, and then use it, and then that you're going to be all set. And so that's it for our that. So now that we've downloaded Pinot and at least know how to, now let's talk about protein folding. So what is protein folding? Well, protein folding is where the fun part begins, the main part about proteins. Now, cows have specialized stomachs called rumens. You've probably heard of they have 4 stomachs, which is just a really large stomach that's divided. Rumens are home to bacteria that help cows digest plants. These bacteria produce special proteins. So, proteins are large amino acid polymers, which I hope you do remember from episode 8. Now, there are episode 6, sorry, I got confused. The 203 amino acids above make up a protein called a cohesion. That's part of a bacterial enzyme found in the stomach of cows. Cows and many other animals use rumen bacteria and their enzymes to help them digest plants. So here, as you can hear, the long letter MAALTDRGMTYDL. I'm not going to read that. Now you notice that the beginning is spelled malt and the C terminal amino acid spelled gap. Now this little squiggly line you see here, which you probably have noticed from the hydrogen bonding, that means it goes on after this. It's not just that it goes a really long time. And as you can clearly see here, malt, blah 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 blah, 196 amino acids, and then we have gap. That means proteins are very long. How does it fold into the proper shape? Now, we don't actually know that, and that's the main question of this. This is ID to a new fold. Folding is this 3D shape of a protein. So there are different types of folding. There is primary structure, secondary structure, tertiary structure, and quaternary. We're going to get to those later. A rainbow version shows how the protein relates to the amino acid sequence. Now you might have noticed that the beginning malt and the end gap are together. This is very, very common for a lot of proteins. So just so you know, this is the thing that is common for most proteins. We'll focus on the colored areas of the protein to answer this question. What do the sheets and spirals mean? Now, these are these look pretty fun, but they're not just some tangly fun. It's really important. By the end of the lesson, we'll be able to partially answer this question. The specific sequence of dermatological fold. The always fold into the cohesion protein. The hydrophobic will sit inside the protein, and the amino acids that are hydrophilic will point into the water that surrounds the protein. Now, this makes sense, doesn't it? So, clearly, this will be true. Different hydrogen bonding platforms and sheet-like structures or can carry into helical spirals. In previously, we have seen how peptides can hydrogen bond together. So, this is known as a beta sheet, as you can clearly see. The O hydrogen bond twists the N on H. And the special hydrogen bond is called an antiparallel because they're sort of like inverted, so it's C to N, N to C, C to N in the terminal sequence. That only with the polarized H on N. So here are the the hydrogen bonds. Beta sheets are represented by flat arrows which point to the C terminal direction. You can clearly see here. To symptoms that the atoms and bonds, but it's important to remember that there are not actually real arrow-shaped sheets inside proteins, only bonded atoms. Here are they. In sheets, hydrogen bonds connect and fold distant, far parts of the polymer together. This is secondary structure on the agenda. And now that makes a part. Now, as you can clearly see, there are a lot more back over here. And here. By distant parts, we mean the first ones as in the polymer sequence. You then says close to one another due to hydrogen. Now, Lakai is my favorite out of these. So look, there's a beta here, a small one here, one here. They're like everywhere. Since the protein is large, there are many other hydrogen bonds to fold up the protein. So, as you can see, there are many other hydrogen bonds. Now, this is a really sort of complicated mess. The cohesion protein is rich in beta sheet, which are these arrows. I don't know which one was my pointer. The circular hydrogen bond is called an alpha helix. Notice that only pair of hydrogen bond with the polarized H on N. So here's the hydrogen bonds, but however, they do near parts or close parts. Alpha helixes are represented by spiral ribbons. Now this is actually really cool to see. But and by the way, there's also this the sort of assignment that I do encourage you guys to do. So I will be posting the video after this. But however, here's a preview of it. So figure 1, close-up image of the heme of oxymyoglobin with residues H64 and H990 and sulfur ion highlighted. There are 2 of these. Now this is just the first one out of the 2 that I have. So you can use Pages or Word. I don't have Word. I do, but I didn't have it when I was doing it. So here is it, and that is about it. And the helix contains and folds the nearby parts of the polymer together. That means the parts that are close together. You can clearly see here, the beta sheets form 100 connect distant parts of the polymer. Alpha helices form 100 contain nearby parts. So remember that in mind. By nearby parts, we mean only a few positions from each other, and the polymer connects through hydrogen bonds. So here are all the beta sheets and alpha helices. But how do these 203 amino acids know how to fold? Hydrophobic amino acids fold to the inside of the protein because the outside is water, obviously. Hydrophilic amino acids fold to the outside protein because they like to hydrobond with the surrounding water. And so here, remember, alkanes are insoluble in water. Colored green. Avoid the green is used to confuse with fluorine atoms. Small liquids that's origin in nature are water soluble. So here, full of these. That's no similar. This does not mean that the subs or the hydrogens make hydrogen bonds. So here are the answers. Now, protein folding of cohesion. The backbone of our cohesion protein showing sheets and helices. You now know a lot about proteins. Try the first 2 YouTube Primal videos on proteins and protein folding, which I just talked about. The videos don't mention hydrophobic and hydrophilic organisms, but see if you can find and color them. And that's it, and we see you later. Bye for now.